Hello everyone, welcome back to our class. We continue to study Chapter 9, Convection. Section 2. In this section, we will build the boundary layer equation. Boundary layer equation certainly is very difficult to obtain. But at the last section, we studied the boundary layer. We have thermal boundary layer and velocity boundary layer. In boundary layer, for laminar flow, we can take one very small to analyze. For example, we take this element to analyze. The height is dy, the width is dx. In this boundary layer, we give some assumptions. One, the body force is negligible, no force in the working fluid. There is no thermal energy generation in the flow. The flow is no reaction, no chemical reaction. So it's simple working fluid. The boundary layer thickness are very small relative to the size of the object, and the y direction, velocity, and the temperature must change from their surface to their free stream. In this region, the change is very big. However, in x direction, the change is not so big. So in y direction, the change is small, with the distance. Therefore, the gradient normal to the object's surface are much larger than those along the surface. We can neglect some terms. For example, the partial u power second, partial x power second certainly is smaller than partial u partial y power second. Y direction, the change is larger. X direction, the change is not so big. Also, the temperature in x direction, the partial t power second, partial x power second, certainly is smaller than partial t power second over partial y power second. In y direction, certainly change very, very big. X direction, the temperature change is not so big. Also, partial p over partial x equals partial dp infinite over dx. In x direction, the p, the change is not so big. It's not so big as the very long distance. So we can do some assumptions, three equations. If we have the assumption like this, we can get overall continuity equation. We obtain the continuity equation. Here v is velocity in y direction. So partial u partial x plus partial v partial y together is 0. Because of this equation, we can call it continuity equation. Also, x momentum equation, u partial u over partial x plus v partial u partial y together, momentum equals minus 1 over rho is density, dp infinite over dx, plus mu power second u over partial y power second. Here is the momentum equation. The last one is energy equation. U partial t partial x and mu partial t partial over partial y equals alpha partial t power second over plus y power second plus v over cp plus t plus y together power second. Here is the energy equation. So for the elements in the laminar flow, we obtain the three equations. Here, alpha is the thermal diffusivity. The unit is g/meter per second. So, because these three equation is very common, it's very difficult to solve it. So, we do some normalized boundary equation. We can do some change. First, we defined the dimensionless parameters. For example, x star equals x over L is x star. Y star equals y over L become dimensionless. Where L is the characteristic length for surface of interest. At the same way, we can define u star equals u over u infinite. V star equals v over u infinite become dimensionless. Last one is dimensionless pressure. P star equals P infinite over rho u infinite power second. No dimension. So we give some definition. Become no dimension. The parameters become dimensionless. Normalized boundary layer equations. From the last page, finally normalized boundary layer equation is obtained. Firstly is velocity boundary layer equation. We obtained this equation. It's very long. Every parameter includes some star. U star, X star, Y star, P star, X star. But here more number. We can call it Reynolds number. The boundary condition is U star, X star, Y star is 0, equals 0. U star, X star, Y star is infinite, is 1. V star is 0. Re is a number. We can call it Reynolds number, dimensionless number. Its definition is REL equals U infinite times L over mu. Here is mu. The thermal boundary equation, we do some change. Any parameter become parameter star. For example, U star, T star, X star. Here's V star, Y star. But in this equation, more two numbers is Reynolds number and Planck number. Reynolds and Planck number is in the equation. Planck number is defined as PR equals mu over alpha is Cp mu over K. K is conductivity. Here is mu. Mu is viscosity. Functional form of solution. Because the equation in the last page, the equations is very difficult to solve. So we can do some guess. So functional form of the solution. We can guess the solution. From the dimensionless velocity equation, we can guess the solution to have the form of this equation. U star equals f x star y star and Reynolds number and dp star over dx star. 1, 2, 3, 4. 4 parameters the function. dp star over dx star represents the influence of geometry on the velocity distribution. If we have obtained the solution of U star, then we can guess the form of T star solution. Certainly, T star equals the function of x star, y star, Reynolds number, Planck number, and dp star over dx star. It also is 5 parameters, the function. For prescribed geometry, T star will have the relationship with dp star over dx star. Have the relationship. Certainly, relationship. These two solution is our guess. It's not a real the solution. Just a guess. Okay. About the two numbers of Lucet number, Reynolds number, and Planck number, we can give some discussion. The first number is Lucet number. From the definition of convection coefficient, last several pages we have obtained hx equals minus kf over ts minus t infinite times partial t partial y when y is 0. Certainly we can do some change, use the dimensionless parameters. So finally we can obtain hx equals minus kf over L times t infinite minus ts over ts minus t infinite times partial t star over partial y star when y star is 0. Obtain this term. So K is the working fluid, the conductivity. L is the characteristic length. Here's partial T star, partial Y star. We obtained here is the dimensionless differential. So we can give some definition for the conduction number. Conduction number is Lucet number just is hxl over kf. Here is a dimensionless number, dimensionless parameter. So we use this dimensionless differential to represent a number. So the Lucet number just is partial t star, partial y star when y star is 0. Just is this one. So its definition is hx times L over kf. Kf is conductivity. To define the dependent dimensionless parameter Lucet number just come from this equation. Okay. Therefore, for prescribed geometry, for defined the geometry, we have Lucet number is a function x star, Reynolds number, and Planck number. 3 parameters, the function. So Lucet number equals f is function, x star, Reynolds number, and Planck number. Because the average heat transfer coefficient for hold the surface is obtained by integrating hold the surface for the body. It must be independent of the special variable x die. No relationship with the x die. Hence, Nusselt number average for whole the body is H average times L over Kf. So it is only the Reynolds number plus number the function. So we can guess the solution like this. Solution. This is just the result we need. We can obtain this equation. This equation is our guess. It's not a real solution. Here we can give some discussion about the very special the number, Nusselt number, Reynolds number, Planck number. Certainly, these three numbers have some physical meaning. So, the physical interpretation of the dimensional parameters, we can give some discussion. Firstly, is Nusselt number is the ratio of convection to pure conduction heat transfer. Just is the ratio convection to the conduction heat transfer. Pure conduction. The Reynolds number is the ratio of the inertia and the viscous force. Just is the ratio. Inertia, the force, and over the viscous force. Planck number is the ratio of momentum and thermal diffusivities. Here we should give the noticeable. Planck number strongly influence the relative growth of the velocity and the thermal boundary layers. Similar delta over delta T is proportional Planck number equals PR power nth. For gas, maybe delta is similar with the delta T. For gas, maybe it's similar, but for liquid, it's different. The second, we can do some think out of solving the problems, because convection is very difficult to solve the equations, very difficult. But we can do some think out about the problems. Generally, we use 5 steps to solve the convection problems. Firstly, to determine the characteristic length L. Firstly, we should to obtain the length L of the problem. Secondly, to determine RE and PR number, Reynolds number and Planck number, we should obtain. When we obtain Reynolds number and Planck number, the third step to determine the Nusselt number. Firstly, to calculate the convection coefficient H, because the coefficient always relationship with the Nusselt number. When we obtain the Nusselt number, certainly we can calculate the coefficient H. Fifthly, based on the Newton's law, to calculate the heat transfer rate, because Q always equals H A times temperature difference. Generally, temperature difference is easy to test, to obtain. A is the area, is also easy to obtain. So if we obtain H, certainly we can use this equation to calculate the heat transfer flow rate. Okay, we simplified to to get the 5 steps. Firstly, when we obtain the program, certainly we first step to obtain the characteristic length and calculate the mean temperature, because the free stream, the temperature and surface of solid, the surface, the temperature is different. So we should calculate the mean temperature. From the mean temperature and the characteristic length, we can determine the Reynolds number and the Prandtl number. After obtaining these numbers to determine the flow mode, laminar flow or turbulent flow. When we obtain, we know this term, this flow is laminar flow or turbulent flow, certainly we can calculate the Nusselt number. From this Nusselt number, we can calculate the heat transfer coefficient, H. From Newton's law of cooling, the equation to calculate the Q. That's the solution. Okay, thank you very much.